third lecture of Johannes Henn. Thank you very much. Good morning, everyone. Welcome back. So let me start with just a quick reminder of what we did last time. So we were looking at tree-level scattering amplitudes of gluons, and the first part of yesterday we spent some time in organizing the calculation, somehow dividing things up to make our life easier. And one important step was the color decomposition of the tree-level amplitudes, where basically we have the full amplitudes which depend on color, depend on kinematics, depend on helicity configuration. And we were able to factor out, in some sense, the color information. It turned out that at tree level, one can always achieve this form where one has single traces of the SUN generators, and then something called partial amplitudes. And the advantage is in that formulation, the partial amplitudes, they then no longer depend on the color, but they only depend on the kinematics and on the helicities. So this is a useful decomposition. Moreover, I didn't prove, but I commented that these partial amplitudes, they also have nice, somewhat nicer singularity properties, namely that poles can only occur in adjacent momenta, or rather in sums of adjacent momenta, when something like pi plus pi plus 1 and so on, the whole chain of momenta squared goes to 0. And this is different from the full amplitudes, which can have singularities in any momentum channel. So this is a bit, this is useful, and then later we used that property when we thought about recursion relations, when we thought about complex shifts. We found that this led to fewer poles in the complex plane, so more compact, shorter formulas we could write down. So then these, in other words, it's sufficient to know these partial amplitudes to reconstruct the whole amplitudes. I'll actually say a bit more. It turns out that one doesn't need all of them. They're not all independent. So in some situations, it's actually sufficient to just know a few of them, and then from that information you can reconstruct the other ones. Now further, then I gave you a few examples of amplitudes. I told you that for certain helicity configurations, the all plus helicity configuration and single minus helicity configuration, the amplitudes actually vanish. So they're the simplest amplitudes. That's true at tree level, or if you're in a supersymmetric theory. And then at tree level, the first non-trivial amplitude is the Amici amplitude, and that one, it's non-trivial, but it turns out that one can actually write it in a single line, and so this is the formula for n particles where the negative helicities are positioned I and j. And as I told you, the goal will be to be able to reproduce this. So in fact, you'll be able to use the BCFW recursion that we discussed yesterday to prove that formula by induction. And so the goal of today's lecture is to give you the final ingredients that you need to actually carry that out. So yesterday, basically, we went through the idea of how this complex deformation works, how we relate this amplitude to certain residues in the complex plane. And so that's the main idea that you already understand. Now today I'm giving you a few, let's say, necessary technical tricks for how actually to work it out. As usual in life, there's some subtleties, and so I'll show you what these are about. All right, good. Any questions so far about what we did yesterday? I'll put this down so you don't have to be afraid. Okay, so then let me continue. So the first thing I'd like to comment on is on the partial amplitudes. I just told you that in fact not all of them are independent. So let me comment on certain relations that exist. So not all partial amplitudes are independent. So the first point is we have a symmetry. So on the left-hand side we have an amplitude which is the scattering of n gluons, So that obviously has a permutation symmetry. You can just relabel, exchange positions and relabel the gluons. Now on the right hand side, what happens to this permutation symmetry? So these single traces, they actually have a cyclic symmetry, the property of a trace. So therefore, that cyclic symmetry is still present in the partial amplitudes. So that we can still use. So that the partial amplitudes have to be cyclically symmetric. Okay, then further, there's something that actually we used already. I gave you a little exercise yesterday in for the 4-point MHV amplitude. We said it's the plus plus minus minus amplitude. You can think of it as a function of the lambda spinors or as a function of a lambda tilde spinors. More generally, if you apply parity, you can flip all the minus and plus helicities. So you can relate them to each other. So in general, the parity relates the amplitudes of flipped helicities. So reverse all helicities. Okay. So these are pretty basic. Now. Yeah, there's a more interesting identity, and that I also briefly mentioned yesterday, the so-called photon decoupling identity. And more generally, these I would call them group theory identities. Now, the idea is that the decomposition formula up there is we wrote it down for SUN, but it's also valid for UN theory. So it's I didn't give it a name, but so the color decomposition formula is also valid in a UN theory. So this means that to SUN you basically add a diagonal element that corresponds to the photon. But okay, that's the first thing. So we have these amplitudes which now may either correspond to scattering of photons or gluons or some mixed objects. But now we also know that at tree level, if we scatter photons of gluons, these amplitudes must vanish because there are simply no interaction terms. You'd have to have some fermions that allow them to couple with each other. So in other words, we know if we look at one of the but we replace one of the T's by the generator corresponding to the photon, which is a diagonal matrix, then the amplitudes must vanish. And so this immediately gives you some identity. And so it's this read. So we have 0 equals to the following. So what we can do is we can say we take particle n to be the photon. So that then drops out of a trace, and then we have a bunch of terms which correspond to all the non. Sorry, how did I write it here? Yeah, all the permutations of the other particles. Can't seem to make sense of my notation. Sorry, I just don't want to get confused in the notation, so I think I'll better just write it out in the book. Let's see if that's certain. Right. I'm sorry, I was just sorry for the confusion. I was just telling you your nonsense. So we take one particle to be the photon, and different from what I was saying. Now the the photon, whatever it is, so in this sum here with the sigmas, it can appear at different positions, but then since it's represented by the identity generator, it just drops out of the trace. And so then we have a bunch of traces which are just identical, because you know, it didn't depend on where the identity was inserted. So we basically have a sum where the let's say whatever we named the photon, let's say particle 1, it can appear at any position. So in the partial, for instance, the first term is a partial amplitude where the photon was at position 1, and so all the other particles are in this canonical order. But then we can insert the photon between gluon 2 and 3, and so on. So we get a sum of n plus 1 terms. So let's just write terms and so on. And so let's say it's a term where the photon is the penultimate one, and then also at the last position. Okay. So is it clear? We just have the photon inserted at any position here.
So what is the apply for each other to extend one
Yes. So I mean, this is an example, but of course we still have cyclic symmetry. So you can any of these amplitudes are cyclically symmetric. So you can just still apply that. Now, okay, so this is this is already a number of identities. Yes, so then there's one more. I just put it here. There's the reflection identity. So if you just reverse the ordering, so 1 through n, instead of considering that, you start with n minus 1 to n. This is also, these amplitudes, these partial amplitudes are also related, and this follows, like these other things, follows from the Feynman rules. So we have the following identity. So A 1 to n is equal to minus 1 to the n. It's the amplitude where I start with n and minus 1 all the way to 1. All right, so you see that there's actually lots of relations between these partial amplitudes, and that means that in general you don't need to compute all of them individually. Sometimes it's sufficient that you just know 1 or 2, and then you have all the information you need for the full amplitude. The simplest case, let's just look at this in some example. The simplest case is the 4-particle scattering case. In fact, here I've already given you everything you need to describe the entire amplitude. Because, well, what do we have? Let's start with different holistic configurations. We can have the all plus amplitude, but that we know it vanishes because it's this all plus case. Likewise, the conjugate has to vanish because it's because of parity. And then we have the single minus amplitudes. So first of all, there's 4 because the minus gluon could be in any position. But so we'd even just need to know 1 of them. But in fact, we know that they all vanish again through supersymmetry. And the same is true for the parity conjugates. So these are all 0. So this means that for 4-particle amplitudes, actually the only amplitudes that we need to consider are MHV amplitudes. So then we have the MHV ones. Now for both, I already gave you a formula actually for arbitrary locations of the negative holistic gluons. Now it turns out that through these identities, this is actually even too much information. You wouldn't have to know all of this. it's sufficient actually to know just one of these MHV amplitudes, thanks to the identities that we have here. This is something you can convince yourself. For example, if you look at the photon decoupling, you get a nice identity like so. So this identity, you can use it to relate different MHV amplitudes, because we have, let's say, we take minus, minus, plus, plus in the first term, and then what's this term? It's plus. Sorry, this one. So here I just exchange minus 1 and 2, so that's the same. I just write it up here. Minus, minus, plus, plus. So then we have minus, plus, minus, plus, minus, plus, plus, minus, for instance. And then, of course, moreover, so one thing you see, it allows you to it allows you to relate amplitudes where you have the negative helicity gluons adjacent and split. Moreover, you have the cyclic identity, so that, for instance, a term like this, you can relate this amplitude here to that amplitude over there. So it's very clear that with the set of identities that you have, that's you just need one amplitude, and then you can generate all the others. All right. So now I'd like to give you one homework, which can also serve to warm up a little bit more with these spinners. These, for some of you, they're quite new. So here you have the general formula actually for the MHV amplitudes. What I would like to invite you to do is actually use that and try to verify this identity. It's not too difficult, but you need to, I think it's useful. You will need to understand one or few tricks, some Schouten identity or some trick with momentum conservation. So this will actually come in very handy later when you use the DCFW recursion relations. So it's a very useful exercise to check this. All right. So now, having talked about these partial amplitudes and how you can go from them to the full amplitudes, I'd like to discuss a little bit more about the helicity classification, because this turns out to be a useful guiding principle in the sense of starting with something simple and then computing the amplitudes that are more and more complicated in several steps. In a way, we started like this. We said the very simplest amplitudes are 0, the all plus amplitudes, single minus amplitudes. Now we have this simplest MHV amplitude, but how does it continue? So what's the picture here? So let me draw this here. This will be the helicity classification. So I'd like to consider some amplitude with where I label the number of particles n as usual, and I'd like to introduce another number k, which denotes the roughly speaking the number of negative helicity gluons. So there's this notation. So we have the MHV amplitude for n particles. Now. So this is the amplitude of 2 negative helicity gluons. Now there's something that people call next to MHV. So this is something where you have 3 negative helicity gluons, and sometimes this is abbreviated just with an n, like n MHV. And following then this notation, we have the nk MHV. So we have where the number of negative helicity gluons is just n plus 2. and the rest is plus holistic gluons.
Should be okay, that one, right?
Thank you, yes, that's okay. And the total number is n. Thanks. Right, so we'll use that notation. So I draw a plot with n and k essentially on the axis. So let's do this. So I like to have n on the vertical axis, and on the horizontal axis I'll put a combination. We'll see that'll turn out to be nice. Just for aesthetics, we put n minus 4 minus k, and well, no particular reason, but it just will make the plots a bit more symmetric. And so with this convention, so if we have so also let me put some labels here. So this will be 5 particles, 6, 7, 8 particles. Somehow 2 to 2 amplitudes, 4 particles I'll take as the origin, and then we'll draw something symmetric. 1, 2, minus 1, minus 2 here. So what does the origin mean? So n equals 4, k equals 0. So this is actually the MHV amplitude. MHV 4-point amplitude. MHV 4-point amplitude. Now, let's see if we can find these MHV amplitudes, also all the other ones. So we will have an infinite number of them, so as we increase the number of particles. So we go up, but then also here we go up because k stays 0. So this will just be an infinite 0, which is here on the diagonal. So this is a whole infinite series of the, I'll encircle them, just denote them like this. These are the MHV amplitudes. Now, I told you that in a way the 2 to 2 amplitude is really the basic amplitude. However, there's a certain subtlety, and we'll see momentarily that there's also actually a 3-particle amplitude that will be quite important in the discussion of the recursion relations. So I just like to anticipate it here and draw this dot. So this will be something a bit curious with 2 negative and 1 plus helicity gluon. If you think about it, it doesn't make any sense, but right now. But we'll see how it can make sense. Anyway, in the same sense, there's a conjugate of this, which is the MHV bar 3-point amplitude. So this will have plus plus minus helicity. Again, these don't worry about them too much. Don't worry about these 3-point amplitudes now too much. We'll see momentarily what they mean. Okay, but now let's go into more familiar directions. So these were MHV. So what do the next to MHV amplitudes correspond to? So for that we need one more negative helicity gluon. So one thing we can do, we have this 5-particle amplitude, so that's minus minus plus plus plus. We can just consider the conjugate, so that's minus 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 plus plus. So this is in fact the first non-MHV amplitude. It sits over there. So it's a next to MHV amplitude. So minus 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 plus plus. But it's also the conjugate of this one. So one could also say it's MHV bar. And now, like the MHV amplitudes, here there's an infinite band where you just go diagonally up. So there's also a 6-particle one, a 7-particle one, and so on. So this is an infinite band right here. So this would be the next to MHV, and so on. So now this diagram continues. If you had 6 particles, you have 2 negative helicity gluons, 4 plus helicity gluons. We can just conjugate. Here the 6-particle MHV bar amplitude would be here. So this is also next to MHV amplitude, and this is the starting point for another infinite band, which goes up like this. So So with 6, 7, and so on. All right. So I think this is useful to keep in mind for two reasons. One reason is that, in fact, for low number of particles, it shows you that, in fact, you don't need to go very far in this non-MHV direction. Because let's say you're interested in 6 particle amplitudes, 2 to 4 processes, already a lot of particles actually. When we see, well, up to 6 particles, we have all these MHV amplitudes. We have one non-MHV amplitude right here. And the other amplitude is actually just a conjugate of MHV. So in this sense, if we stop here, we just need to know about MHV and next to MHV amplitudes. And luckily for us, these will turn out to be the simplest amplitudes. So, roughly speaking, as you go higher up in this direction, not so much because of n, but just because of this non-MHV-ness, things get a bit more complicated. So it just tells you for practical purposes, it's actually, it actually makes a lot of sense to follow this holistic classification. Now the other reason why it's useful to keep this in mind, it has to do with the way we can think about solving for the amplitudes in the context of BCFW, where we will see that we can start, in a way, solving things in 2 steps. We can first consider the MHV band and kind of start computing the 4 particle amplitude, 5 particle amplitude. Then imagine a recursion in n, where we just in one go compute this whole band, arrive at that formula up there, or over here. And then having that, we will see that actually that is then an ingredient, like some seed for the next to MHV recursion. And so having computed this, then you can try to understand the structure and attempt to solve in one go the next to MHV band. And in principle, so on and so forth. And this strategy actually has been implemented, and in this way you can get closed form formulas for all of these different bands. All right. Any questions on this classification? All right, so then let's return to PCFW, to our recursion relations, and to really make them work, I need to tell you a bit about these kind of exotic 3 particle amplitudes. What are they? How are they relevant? So we'll talk about 3 particle kinematics and amplitudes. So in fact, the very reason that these 3-point amplitudes exist has to do with the fact that we're dealing with complex momenta. Remember that an essential ingredient in writing down the recursion relations was to introduce this complex shift Z, which allowed us to do complex analysis. And if you wish, the price to pay, and well, it's a useful thing. It's actually, I think, a small price. This price to pay is that we have complex kinematics. And this is at the root of the fact that we can actually talk about these 3 particle amplitudes. So, in fact, let's see. Yeah, let's talk about the kinematics. So we have our 3 particles, 1, 2, 3. And we have actually a lot of constraints. That's why this usually is something that we would not consider. So we have the momentum conservation as a vectorial equation. And we have also the on-shell conditions. So P1 squared is 0, P2 squared is 0, P3 squared is 0. So now, okay, you could think about what are actually the variables that are left. How can we solve these constraints? And so one thing you can do, you can put P3 on the other side and square the relation. And so then you learn that P1 plus P2 squared is equal to 0. But the squares also vanish. So from this it follows that 2 times P1 plus P2 is equal to 0. And the same for all the other scalar products. So now if we have real momenta, the only way to satisfy these constraints is to say that, well, all these on-chain momenta, they have to be collinear. So if P1 is proportional to P2, then this can actually be 0, and so on. So for real momentum, it follows that P1 is proportional to P2, proportional to P3, proportional to some light-like momentum, and then this relation is satisfied. But then this tells us that we're not in a generic situation, that we cannot consider non-trivial free particle scattering. That it tells us that this amplitude is really degenerate. So that's why usually one would not consider this. But now the situation changes thanks to the fact that we consider this in complex kinematics. Basically, what changes is that there's a non-trivial solution to these equations up there. So if we take the first equation, what it means in our spinor notation. So let's say the situation changes for complex kinematics. So if you take the first equation, it reads like so, and similarly for the other ones. Now the point is that we can solve this by either saying that this lambda bracket is 0 or the lambda tilde bracket is 0. So we can say 1, 2 is equal to 0, or square bracket 1, 2 is equal to 0. Now, like with the momenta, for the spinors, well, here it's more direct. If this bracket is 0, then it means that the two lambdas are proportional to each other. So in this case, it means that lambda alpha 1 is proportional to lambda alpha 2, and so on for the other equations. So what we see here is that we can satisfy the constraints by saying that either all the lambdas are proportional to each other, or all the lambda tildes are proportional to each other. And now, why is this different from the real case? Well, for real kinematics, in fact, the lambdas and the lambda tildes, they're related by complex conjugation. So if the lambdas are proportional to each other by complex conjugate, it must be true also for the lambda tildes, and then you turn to this statement that the momenta are collinear. But here in complex kinematics, we can imagine a solution where the lambdas are all proportional, but the lambda tildes are unconstrained. And this gives us the opportunity to define some non-trivial free particle amplitudes. So now we have two cases. Two cases basically correspond to the situation where all the lambdas are equal to proportional to each other. So all the lambda brackets are collinear. So this turns out it will correspond to the MHV bar free particle case, and the second case is the conjugate one. So the square brackets are 0. So here in this case the lambda tildes are unconstrained. And here the lambdas are constrained. Okay, now I have a little puzzle for you, because we could think, well, let's consider this MHV bar case. And now the question is, what could this amplitude be? Of course, we could take Feynman diagrams, open a textbook which details how exactly you do this calculation. Let's say so it's MHV bar, so we need two. Actually, okay, we'll get to that. Let's consider MHV because it's more familiar. So let's take two negative holistic gluons and one plus holistic gluon. So in principle, one could compute this amplitude and see what expression one gets, keeping in mind that we have these constraints. But actually, I'd like to ask you now, what if you had to imagine what this amplitude could be? What could you write down? So the task is, can we write down an object which only depends on lambdas and has the correct helicity properties? So in other words, it has to have helicity -1 at positions 1 and 2, and has to have helicity +1 at position 3. Any thoughts?
We could start by writing a product of those three elements, set some parameter for power of these things.
Yes, so this is a very, very good point. So in fact, because the lambda tildes are 0, so the only objects we can write down really are these three brackets. So in general, this amplitude will have to look like this: 1, 2 to some power, 2, 3 to another power in general, and 3, 1 finally. Right? And now, well, it's a bit like in conformal field theory yesterday. Well, Gleb didn't talk so much about 3-point functions, but in conformal field theory, it's the case that for a 3-point function, once you know the scaling weights, the functional form of a function is completely fixed up to an overall normalization. Now here, it's very analogous. Once we specify what the helicity of the particles is, these powers are in fact determined, and the only freedom is the overall normalization. So once you realize this, then you understand that this amplitude is actually unique up to the normalization, and so we could guess what it is, but you could also take a hint from up there. So so it has to be, let's simplify it even a little bit so that it's really manifested in this form. So it's just this, will be just this amplitude here. And you can remember, if you remember from yesterday, our helicity assignments, you can check that. So for particle 1 and 2, it has, on the whole, there's two lambdas upstairs, so that corresponds to helicity -1, and for 2 and 3, for particle 3, we have 2 lambdas downstairs, so that's the correct dependence for plus helicity particle. Right. So what you see is that actually, based on these considerations, you don't even have to do the calculation. Well, you might want to do the calculation to fix the overall normalization, but it really just follows from the in a way from the symmetry properties, from the helicity assignments. And so likewise, we can write down the MHV bar amplitude just by conjugation. So for so let's say for well, I could just write it in general. If we let's say the plus helicity gluons at position INJ, then it's just this to the 4th power, and downstairs we have 1, 2, 2, 3, and 3, 1. So it's just exactly the same story. The dependence is completely fixed by the helicity assignment. All right. Now there's a yes, there's a question.
You're assuming that lambda and lambda bar, they are independent, but for these shifts that we always do, they are not really independent.
You're asking if I'm assuming that lambda and lambda bar are yeah. So I must indeed, for complex kinematics, I'm assuming that lambda and lambda tilde are independent variables. For real momenta, this is not the case. For real momenta, they're related by complex conjugation. But here, importantly, we doubled the degrees of freedom, if you wish. We're considering complex momenta. And in this context, we can write down these free particle amplitudes.
But usually we are right here because we do some shift. It is not any shift, but some particular one. So they are not independent.
Well, later we do this in the context, we look at this in the context of a BCFW shift. It's true here we have not shifted anything. I've just declared that we are considering gluon scattering for complex momenta. And in this case, we can imagine writing down these amplitudes.
And small thing, you could have changed the signature instead of going to complex momenta, so stay in the momenta just simply signature.
Yes, that's possible. One can also view it as working in a different signature. Maybe it's a personal preference. I just like to think about complexification of the momentum. Any other questions or comments? Yes?
So you're using the little group scaling of the amplitude to fix the structure, right? But it seems to me that there is no information about the theory itself. So for example, if I were to add an FQ modification to Young-Mills theory, which would give me a cubic term, how does that influence this reasoning? Does anything change?
Yeah, so you're asking how does this argument know about what theory we're working in? And it's true that it really just needs the information of what particles we scatter. So for instance here we found this amplitude by saying we had a scattering of external gluons, but instead you could have written down something similar if you consider gravitons or fermions or so on, with different Helistia assignments, and you would find slightly different but still fixed formulas. So in this sense, these amplitudes are universal. That they just follow from the Helistia assignment of the external particles.
So if I were about cube modification, this would not modify the three-point amplitude?
If you I think so. One assumption that went in is that we don't have any other parameters that our amplitude could depend on. So if you introduce effective vertices with some other dimensional full parameters, then I can imagine that you would get something more. I haven't really thought about this, but certainly one assumption that went into here is that these are the only variables that our amplitude depends on. All right. Now there's one more thing that you could have asked, which is that I told you previously that the all plus amplitudes and the single minus amplitudes vanished. And now clearly I'm contradicting myself because we just wrote down a single minus amplitude and I'm saying it doesn't vanish. Okay, so very shocking. Indeed. So this statement up there, this is true, let's say, for real amplitudes, so amplitudes with real momenta. The free particle case is an exception. I told you that one argument leading to that conclusion is based on supersymmetry. And that argument, if you go through it, it works perfectly fine for arbitrary number n of particles. But for n equals 3, there's some special case, which one should consider apart. And if you wish, there's a loophole in this argument. It's a bit related to the fact that free particle kinematics is really special, and so likewise, there's for this argument that the amplitudes vanish is a special case. So please keep in mind that this statement up there is valid for n bigger than 3 particles. All right. so now we have all the ingredients we need to write down in detail, or so that I can tell you in detail how the DCFW equation works, in particular to compute this MHV band. So I just, I didn't write down the BCW recursion relation, but I mean you have it in your notes from yesterday. But now let's write it down and apply it to the specific holistic configuration. So you'd like to find the formula for the MHV amplitudes. For MHV amplitudes. Just to make our life a little bit simpler, let's take the specific case where the negativistic gluons are at position 1 and n. Once you understand the basic principle, it should not make a big difference to also show the other cases. And in fact, if you wish, there's a supersymmetric version of this which makes it really easy. But for the moment, let's consider this case. And also, like yesterday, I'd like to shift now particles 1 and n. So shift gluons 1 and n. And actually, we do it exactly in the same way we did yesterday. So just for as a reminder, write it. So we had P1, the shifted momentum P1 was just P1 minus Z lambda n lambda 1 tilde, and likewise Pn hat was Pn plus Z lambda n lambda 1 tilde. So in other words, the lambda part of 1 gets shifted and the lambda twiddle part of n gets shifted. And I told you yesterday that this is an allowed shift in the sense, well, all shifts are allowed, but for this shift, the term at infinity vanishes. So then we have this BCFW formula where we just have to sum over all the poles at finite distance. And so let me just write this down. So we have our MHV formula. So by the BCFW relation, we get the following formula. The n particle MHV amplitude of the holistic configuration is then given by a sum over the J, which corresponds to all the different poles that we pick up, all the factorization channels. There's also a sum over the helicity of the intermediate state. And then we have these factorized diagrams essentially. J sitting over here, helicity H bar or minus H, 1 and H here. J minus 1. We saw that we always start at 1. And here it's the shifted momentum. And here we have particle minus 1, particle n, and also shifted. This is minus H. And so this is just a picture. What does the picture represent? So it's a product of the shifted amplitude on the left times 1 over pj squared, this propagator corresponding to the channel, and times the amplitude on the right, also evaluated at shifted kinematics. Right? And remember I told you that one of the advantages of this formula is that if we evaluate an n particle amplitude here on the left, the number of particles we need here on the right are fewer. So you can work iteratively. So for instance, you could say, well, let's start with 4 particles and compute 5 and so on. And I think, in a way, if you want to, want to really start from the base, say I'm not comfortable with n particles, you can really do this. You can think about what does it mean for 4 particles, what are the different cases on the right hand side. So in particular the sum will almost disappear, you just get a few terms. And this is very good to gain some intuition for how things work. Now the reason I'm not doing that is that after having gained some intuition, you actually realize quite quickly that it's not a lot more difficult to treat the case of general n. So I just like, in a way for clarity, I like to present that. So in fact, this picture simplifies when we specify to the holistic configuration up there. So far this was actually general, even I wouldn't have had to write MHV, but now it will simplify. So now let's consider the specific holistic configuration. So basically what we'll do, we'll assign the external helicities. These we know because we just fixed them. And then we consider the 2 cases where this is plus minus or minus plus. And then we can look at, well, which of these amplitudes actually exist. Some of them will be 0, and this will give us a kind of a better picture of the case at hand. So then we write this as sum over j. And now let's just write out the 2 cases. So we have minus here. This is always shifted, but now for this discussion it's not so important. We just want to look at the helicities. So let's say we have one case where this is a minus and this is a plus. And then we have all the pluses here and the minus at leg n. And then we have also the other case where we just split this to plus minus. Okay. So, need some space. I think I just move this up and then continue here. So while I erase it, take a look and think a bit about what are these amplitudes on the left, on the right? Are they 0? What are they? Are they MHV? Are they MHV bar? And so on. You just try to look at the list of cases that you know, see if you can simplify somewhat this expression. In particular, what about the number j of particles? Can these exist for any j, or are there perhaps some restrictions? So what about the first term there on the left? What do we have? Yes.
Yeah, this should always vanish, except that like the right part is only 3-point amplitude.
Right. So we see that the right amplitude on the right hand side is actually a single minus amplitude. So in fact we know from the SUSY argument that these should vanish. I told you just that there's this special exceptional case for complex kinematics, which is 3 particles. So in fact this means that for the holistic configuration that we have, there's only one term survives here, and it's the term where so there's 3 ones on the right. So the first one is j. So j would have to be n minus 1, and it's just that term that survives in the sum. So we see that. So we have our full MHV amplitude, and so here it's just a single term. So we have minus plus, and I'll denote this by say a filled log. So it's n minus 1 minus shifted to plus, and this is well. So this is n minus 1. So this is n minus 2. So the sum goes away and we just have this single term. Now, what's this notation? I just use this block to denote the free particle MHV bar amplitude, and this one here. Well, for MHV amplitudes, I just do this here, just write it. So, okay, great. What about the next term? What about the term on the right?
Well, you have the same, just as the block on the left side would vanish if you were not three-quarter.
Yeah, that's right. So also there we just have a single term. It's the way it's flipped, except that the assignments are different. So we have this a plus 1, minus 1 plus, and then shifted minus. Okay, so and now this is of course an MHV amplitude. By the way, there we don't have to distinguish so much whether it's free or n particles, because this formula that we found for free particles just fits into this whole all n formula. So the formula for general n for MHV amplitudes, it also is true for n equals 3 in particular. So we don't have to distinguish. Okay, but this is really great news, because we lost this sum, and so you see it's really just a single term, well, sum of two single terms on the right hand side. So now you can kind of imagine how a proof could go. Once you have some idea of what the general formula could be, you use mathematical induction. You say, let's assume that the formula is true for n-1 particles. You plug it in here. You know what the MHV bar amplitude is. Then one needs to evaluate this at the shifted kinematics, substitutes, and sees if one reproduces the desired endpoint amplitude. So this is literally how you can do. And if you're a bit warmed up with this spin-Helisti, you know how to, if you get comfortable with how to plug in this shift, then it's actually not all that difficult. Now I'd like to invite you to do this. There's just one more thing I wanted to warn you about, and this is again a bit subtle, has to do with our free particle kinematics. In fact, the situation is even simpler than this. It turns out that one of the two terms is not relevant for what we need. So there's one of the two terms which is a bit subtle, and so let me explain how we see that. It's in fact related to a question that was asked earlier about complex kinematics and whether we shift or we don't shift. So you see that in this formula, these free particle amplitudes, they are actually evaluated at shifted kinematics. Now let's look at this a bit more detail, and in fact the problematic diagram is this one. So let's look at a bit in more detail. And in particular, I'd like to reinvestigate the free particle kinematics. So what do we have? We have this internal line, which is on shell, and then we have the line with n-1 and the line with n hat. So we know the MHV bar free particle amplitudes, they just depend on the lambda tilde, and they satisfy certain constraints. They satisfy that n-1 n, this hatted quantity, this is equal to 0, and instead that they depend on the square brackets, right? Now I'd just like to investigate what this constraint actually means. Okay? Now for that we need to remember what our shift was. It's written up there. And so let's see, we had the shift for Pn. What does it actually mean? So we had that P hat n is equal to Pn plus z lambda n lambda twiddle 1. So it means in terms of components, lambda hat n, so lambda twiddle n, this is this plus z lambda 1 twiddle. So the lambda twiddle gets shifted. and the lambda actually remains unshifted. Okay, so this is just what we did by definition. But now let's take this and use this here. So the lambda spinner n is actually not shifted, so we can just remove the hat here. So what it means is that n minus 1 n is equal to 0. So okay, previously we said that okay, this is fine as long as we have complex kinematics, and we do want to use complex kinematics as some intermediate tool to compute an amplitude. But at the end of the day, what we compute here on the left-hand side is an actual amplitude that can exist for real scattering kinematics. And in that case, this condition, it would imply a constraint on the kinematics. It would mean that this term is only valid if Pn and Pn minus 1 are collinear. In other words, this term here, it has only delta function support. So it's in a way, it's a distributional term in the for the final external kinematics. So it only exists, only has delta function support. So in other words, if you wish, you could consider this term, but it's something that is more of a distributional nature. As long as the external momenta Pn minus 1 and Pn are not collinear, this term will always be 0. So for a moment, I would like not to consider such terms and just say we compute regular terms. And in this sense, then we can drop this term of recursion. Now you can ask the same argument, what changes when we flip the diagram? Well, what changes is that for the MHV bar vertex here, lambda 1 is actually shifted, and then this condition does not impose a constraint on the external lambdas, but it can be solved in terms of the shift parameter z. So that's the difference. So there it does not create any problem. So instead, we look at this condition here. Then we see that we have 1 hat 2. So what is this? So this has a piecewise, this is just 1, 2, and then we have a term minus z n 2, and so this has to be 0. But now, as I said, it does not have to imply any constraint on the external variable, so simply it fixes z. And this is actually useful in the calculation. So we just have that z is equal to 1, 2 divided by n2. So in summary, the final relation that you have is just this one. You have MHV n particle amplitude, so unshifted, is equal to just a single diagram. 1 n minus 1 and so on. All right. So you just need this one single diagram, and moreover, I mean, you see from this example here also how you actually evaluate it. So this diagram here, it's given by the product of the subamplitudes and at some shifted momentum, and at the location of the pole here, we fixed the parameter z, so it's just substituted in terms of spinners. So in other words, you can already see that this expression here, it is just expressed in terms of the kinematical variables that we use for the amplitude on the left. Alright. So as you could see, there were a few, let's say, pitfalls or subtleties to consider from what you knew yesterday. But I think now with this, you should have all the, all the tools at hand and all the tricks that you need to actually be able to prove the formula. So as I said again, the strategy is to use mathematical induction. You would say, so So the plan of the proof would be first to say you want to show that the formula for an for some low value of n, for example, for n equals 3, this we've already done. We saw that this follows actually from the helicity argument. So there was a single amplitude we could write down. So this is fine. Then as usual, you assume let's say a n minus 1 is okay, and then you do the induction step. You show that a n follows from this. This, which you do thanks to the BCFW formula. And so then, since the formula is true for n equals 3, and since you can always increase n, then you've proven it for any n. So that's the strategy, and so that's what I'd like to give you as a homework. So if you like, think about it, and you can of course come to me if you have any trouble or any questions how to do it. Any questions about this?
So, if I want to calculate the cross section, do I need to take into account that term, like when the n and n minus 1 are collinear, like I don't know, scattering is dual and then pair is like more. There's higher probability to.
Yeah. Okay. It's a very good question. So here. If we, to be honest, I think it's very good to ask such questions because there can be subtleties, especially with distributional terms, and then, so that's also another reason actually why I wanted to discuss it in detail, because it may be that, say in your research, that this could come up, that you have some situation where it becomes relevant. So of course it could potentially become relevant if you need to integrate over something. I don't know, to be honest, in the specific case of a cross-section. So when you might hear from this in other lectures that at loop levels, then you need to evaluate integrals over loop momentum. So that something gets integrated over. And there's also the so-called real and real virtual corrections, where one has a tree-level amplitude, but needs to integrate over phase space, so that there's further integrations. So there could be such subtleties. In particular, how do the amplitudes behave in the collinear configurations, where one does want to control that. But there's also a bunch of other subtleties, such as how exactly do you regularize divergences? Do you deal with the external particles in a 4-dimensional way, or do you put them in d dimensions, for instance, in the context of DIMREG? So yes, so I can't give you a concrete answer on this, but it's very good to keep such things in mind. Yeah.
I think I'm a little confused there with that fixing of Z there. If I remember correctly, the last time I talked about the BCFW reduction. When one wants to look at the non-reduced amplitude at Z equals 0, didn't that fix already the Z in partial amplitudes? So how does this go together with this fixing?
Yeah, I think there's different sets. So we had let's see that we had this picture yesterday. So we started saying a of 0 is, we get it from this integral here, which was the integral of dz over z, a of z, right? Where we evaluate this at 0 basically. So that z is set to 0, but then we said, oh, but this is equal to all the residues at all these other locations, and these were evaluated at zj, where j corresponded to the sum of momenta that had to go to 0. And so in that language, what we're doing is we have now j was fixed now. I think in yesterday's notation it's something like 4 or 3, probably 3, and then z3 is given by that formula.
Okay, we wrote it's actually the same result. Okay.
Yes. So maybe another way of saying that, you might be surprised that it looks like this. Yesterday we had a more general formula for arbitrary number of sum of momenta here. For sum of 2 momenta, the formula simplifies somewhat, and we just have this expression in terms of angle brackets. Yes, sure.
Well, back to the first question. You also mentioned yesterday, Johannes, that the Park-Taylor formula already captures the similarities, the correct three-level similarities, the soft and the collinear, and also can be derived from Feynman diagrams. So I would presume that the first endotherm dropping of distributional nature doesn't really exist there in the final result anyways. So there should be some further argument why this thing in the end cancels out, I would think.
Okay. Well, so yesterday when I made this comment, I certainly was not thinking about, it was not in my mind to talk about distributional terms. So this, now, but you can ask, I think it's, as I would still say, the safe answer is it's a bit subtle. Now, just to give you an example where you might want to consider this, is when you, there are certain situations where it can really be important how exactly the amplitude behaves near these singularities. And this is when you, something that we'll do tomorrow, when you check differential equations on amplitudes. In particular, when you want to check certain symmetries, like conformal symmetry. And again, I would say that in 99.9% of situations when people discuss tree-level amplitudes, they consider them in something that mathematicians would call generic kinematic configurations, that you just, away from any special singular surfaces. On the other hand, we know it's sometimes exactly the interesting situations in physics, like think of Laplace equation. You have a Laplace operator acting on 1 over x squared, and you would say, well, in the general case it's 0, fine, but you know that there's a delta function and it can actually be quite important and interesting. And so I see this in a similar light. So that there can be situations where this actually becomes relevant. And yeah, I don't know what kind of in first principles, if you maybe you could go to some axiomatic quantum field theory and say, well, are there delta functions or not? What is really the distributional nature of 1 over angle bracket 1, 2? One can ask this question, but I can't give you an a priori answer what it is.
Certainly the Park-Taylor formula does have a divergence when n minus 1.
Oh yeah, there's no doubt that there's a divergence, but for instance, so there's a divergence of the type 1 over x, right? But is there also something like delta of x, or some version of that, the derivative of delta of x? I don't know to what extent this has been studied. I think there's a question here.
Is there an example here when choosing the relationship between lambda p and lambda negative p? I mean,
yeah, I think I understand your question. Let me try to repeat it for the others. Yeah, so you're asking about the intermediate momentum here in the diagrams. So let me try to say what the problem is and then how one can solve it. So here we have some momentum which we can call P, and remember that we defined our amplitudes as always for outgoing momentum. So for one of the amplitudes it will be P, for the other one minus P. Okay. Now what P is very clear. It's just given by momentum conservation. For example, this one is just equal to the shifted P1 plus P2. But now in the expressions, when you put together this, you will not find P, but you find the lambdas corresponding to it. Now, the short answer is what you can do is you can always multiply with some, multiply with 1, where you have some bracket in the numerator and the denominator. In this way, you go from the lambdas back to P. You can reconstitute P. And in fact, it's a guarantee that you can do this because the expression is homogeneous in this lambda P. So the simplest way of dealing with this problem is to do that. Then you deal with P and you can just substitute. You can just substitute the definition of what P is in terms of the shift. So another question?
So if I now consider theory with 4-point x, then I can use this formula to reduce the 4-point amplitude to 3-point amplitudes. So this would,
That's
and
great.
they know the 4-point, the 3-point is only. So Does this mean that in any theory I can always reduce the 4-point vertex to 3-point vertices?
So first of all, yes, what you said is true. To really, at a fundamental level, if you go back to this diagram, the only thing you need to start this recursion and to compute all tree-level amplitudes is the bottom line. You need the 3-point MHV and MHV bar amplitudes. We said we fixed those from symmetries from the Listi assignments. And then, as long as the BCFW formula is valid in the form that we had, so meaning that we just had these poles at finite distances and we could throw away the term at infinity, given that that's the case, you can build up everything. So this is, I find this very beautiful because it's really a minimal information. You don't need anything else. There's the other aspect that you can actually in practice solve it quite easily. But yeah, I think it's a very nice comment to make that this is so. Now you have some other theories where you may have an amplitude which does not vanish at infinity, like 5⁴ theory, where then there's some extra information also included. So with that restriction, the answer is yes. Everything, for instance, in Young-Mills, so in gravity theories, everything is constructed from the phi particle vertices. All right.
Further questions? So first of all, let's thank Johannes. There's a few announcements. First of all, for those of you who come with a bike, there's an area with cobblestone area in front of the building that's for delivery. Please don't put your